Ashley gives these talks. I'm the Chief Scientific Officer and one of the co-founders of Fauna. So to start, we first sequenced the human genome over 20 years ago. That was back in 2002. And this was supposed to be the revolution to really curing our diseases. And now we've sequenced millions of human genomes. But if we look, if we look at what killed us 40 years ago, the same diseases that were in the top 10 40 years ago are still the same diseases killing us today. So we're thinking at Fauna Bio that human genomics, it's powerful, but it's not enough on its own. And instead, what we're doing is we're examining animal species that are using the same genes that you and I have to naturally resist and even reverse the course of disease. This enables us to really shine a spotlight on our genomes and the most important parts of our genomes to then target for a broad range of diseases. We have a platform called Convergence, and what we're doing is we're taking insights from animals with these really unique adaptations and then pairing that with human disease data to more rapidly find the most impactful targets that we might just miss with just looking at human genomics alone. And so this gives us a strategy not only on how to develop new therapeutics, but also strategies on how to live longer and healthier lives. Okay. So when you think of animals with unique adaptations for longevity, you're probably familiar with these species, like the Greenland shark, or quahog clam, or tortoises, or bowhead whales, or even long-lived humans. But I hate to break it to you, we're not studying any of these species. Instead, we're studying this little guy, the 13-line ground squirrel. And that's because it can hibernate. So hibernating mammals are special to us because during hibernation, which occurs 6 to 9 months of the year, they can deeply depress metabolic rate, as well as heart rate and respiratory rate to 1% of normal. In the summer months, they'll double in body mass. In the course of 2 months, they'll become quite obese, and then they'll naturally stop eating. And instead, they won't eat, they won't drink, they won't move for 6 to 9 months of the year. And because they can go down to these physiological streams that are basically lethal to us, they have naturally developed mechanisms to resist and repair tissue from damage. And so they're naturally protected from a number of different diseases that we would take on, such as cardiovascular disease, Alzheimer's disease, chronic lower respiratory disease, retinal disease, as well as sarcopenia and obesity. These are diseases that not only affect millions of us, but also or kill millions of us, but they also affect millions of us per year in the US. So for example, when we humans have a heart attack, we have often irreversible damage that'll lead to scar formation in our hearts. These ground squirrels have 25 heart attack-like events every single winter of their lives. And every time they have this event, they take on damage in their heart. Yet, when they emerge in the spring from hibernation, they've repaired that damage, and they have perfectly healthy hearts and go on to live normal lives. And actually, when we look across, well, I'm getting a little ahead of myself, but they live longer than would be expected. And so when we look at the mechanisms that they use to repair and resist this damage, we see that they've optimized many aspects of anti-aging, including during hibernation, they increase DNA repair and protection. They slow epigenetic aging. They also increase telomere, or they elongate telomeres. They also regenerate cells. They reduce cellular stress, and they improve mitochondrial function. So these all hit at these hallmarks of aging. And then when we look across the tree of life, we can find hibernators in every major mammalian clade, even in primates. And when we look at their lifespans, they actually live longer than would be expected, approximately 2.5 times longer than non-hibernators of their same size. Since they're so broadly distributed, we know they're not using any special bear genes or squirrel genes. They're using the same genes we have, just differently. So what we need to do is just find out what they're using and then target them. But how do we actually do that? How do you actually go from animal genomics to an actual therapeutic? So that's where our platform Convergence comes in. We're using animal data, but we're also pairing it with human data at every step of the way using AI and ML to identify these targets. So first, what we do is we identify protective signatures in these animal data sets, and then we compare that to human disease data. Then we map our results, our targets, onto human genomics data to validate, and then we'll validate these in human cell line models to make sure we're actually getting the effect we want to see. And then finally, we can predict compounds that will mimic this natural protection using human cell line models again. I'll get in just to a little bit of the science. This is probably the most scientific part of the talk, but here's an example. This is just an example of how we would find a target gene. So we can use our core convergence module called ORCA to build gene regulatory networks. And in here, in this example, we would go onto ORCA and we'd build gene regulatory networks using our liver transcriptome data from 13-line ground squirrels. And in particular, we're going to enrich for networks that are up or down when the animals are not eating for 6 months of the year, so when they're fasting. Now, we really want to enrich for these longevity genes. So then we'll go and overlay data from other long-lived species. Here, we're looking at genes that are enriched in long-lived naked mole rats. This is just one of hundreds of curated data sets we have on our platform. So we'll run this analysis, and what we'll get is this galaxy of gene regulatory networks that are all differentially expressed both in hibernating squirrels and long-lived naked mole rats. Now we can zoom in on these networks and then look at the hub genes. For instance, this gene here, which we've codenamed FON401G, is really downregulated when animals are hibernating. So all you need to do see is that it's almost not expressed when the animals are hibernating and fasting. It's also downregulated in these long-lived naked mole rats. So we think, oh, this is an interesting gene. Let's go look at human genetics. What's it telling us? Well, we can see that in the human genetics, there's a variant, this A allele, that leads to decreased expression of the same gene in humans. And then if people have this A variant and lower expression of this gene, they also live longer. So we would prioritize this as a core longevity gene that we could then validate. We can also go into directly to small molecules using our platform. So this is where our lead program, FON1083, came from. And it was identified through this analysis of cardiac transcriptome data in the 13-line ground squirrel. Again, we were looking for genes that were co-expressed when animals were undergoing that heart attack-like event or ischemia reperfusion in the winter. And we were looking for genes that were upregulated because we think they would be protective at that time point. So we found this module, which is in red, where all the genes are upregulated. And we fed the top 100 genes from that module into our Leo module, which then takes data from the L1000 database, which has gene expression signatures from 34,000 compounds in 230 cell lines. And what it attempts to do is it matches compounds that produce that same signature of upregulated genes that we input. And so what we get is a ranked ordered list of compounds as our output. And our number 2 compound in this list was called FON1003. So it was a tool compound to a known target. And we did some early validation studies and were convinced by the data that we actually built a whole chemistry campaign around that target. And that's where FON1083 came from, was to optimize the chemistry around the target. And now what we're finding is that FON1083 really halts and slows the progression into heart failure, and specifically heart failure with preserved ejection fraction. It's also slowing the progression from HFpEF to HFpEF with pulmonary hypertension. These are diseases that affect 3 million and 1.5 million patients in the US, respectively. And we know from internal studies that FON1083 improves both mitochondrial energetics and it also suppresses inflammation. These are 2 key elements, both in HFpEF and pH. And significantly, we're finding that FON1083 improves clinically relevant echo parameters as well as exercise duration in our rat models of HFpEF. And we're also finding that that 1083 is resulting in a larger treatment effect that's happening faster than the current standard of care treatments, Jardiance and Entresto. So large pharma is interested in HFpEF, particularly because it's the type of heart failure that increases with age and with obesity. Also, a number of the top pharma are expanding their interest in cardiometabolic indications. And so this is, you can see here, these are the recent acquisitions in the space. And this is just highlighting the potential of revenue generation as these programs enter the clinic and then generate early and positive results in the clinic. In particular, we want to highlight that Corvidia and Tourmaline's drugs both are working to target IL-6 for cardiac indications. We know that Fauna 1083 also suppresses IL-6 when treated on human immune cells. So I'll just give a very brief overview of our pipeline. Our lead program is Fauna 1083. We're initiating IND-enabling studies currently. Our goal is to be in the clinic in the next year. Our second program is in obesity that's partnered with Eli Lilly. We now have a large handful of novel targets that we've discovered. These are truly novel in that they're not incretin-based in their mechanism of action, and we're starting to generate positive in vivo data in our rodent models of obesity at this point. We also have a gene therapy program in retinitis pigmentosa. Again, we're generating positive in vivo data. We have some pharma partner talks planned for the next quarter. And then we just have this just highlights our early stage programs and really the breadth of our early stage programs. But what's fun is we have a couple of programs that are actually funded by NASA because they're relevant for astronaut health as well. We also, our newest iteration of our platform is called Fauna Brain. And it basically takes the power of 4 to 5 drug hunters and compresses that into a few minutes of work. It's a system of AI agents that are now trained to work on our platform and really replicate the process our most experienced drug hunters use to find targets. This will allow us to really broach out into new indications as well as new species. So I just want to highlight that all of what I've shown today was built on this one species, the 13-line ground squirrel. But we're poised to now go into more species, at least 35 other mammalian species we've identified that have natural protective phenotypes. And so I'll finally end just to highlight our team. Myself, I have a background in hibernation biology as well as human genetics. My co-founders have very deep expertise, not only in veterinary medicine, but also comparative and human genomics. And then our head of therapeutics, Brian Berkey, has 20 years of experience in drug development. So he's taken a lot of early stage programs all the way to the clinic. And the interesting thing is that not only has he worked for large pharma, he's also worked for small virtual startups. So he really brings on that expertise we need. And then finally, we have an excellent panel of advisors and KOLs and consultants that are helping us to get to the clinic. And with that, I'll take any questions.
Thank you, Katie. Do we have any questions? Tom, Greg, Tom is over there by the disco ball to the other side, to the left of you. Yes. Oh, yes, he's over there. Yeah, no, I'm telling Greg to bring the mic to Tom.
Thank you, Greg. I appreciate it. Thank you for that wonderful presentation. I really enjoyed it. What are some of the biggest discoveries that you made that may be relevant to human longevity, human health span, that you've discovered from this little squirrel? I find it to be fascinating to be studying animals like this in such a systematic way and to try and pick off a piece here and a piece there to promote human health span. So do you have any kernels of wisdom that you've developed by studying this first animal?
It's a little bit hard to disclose our kernels of wisdom. There are, but so interestingly, we are looking at skeletal muscle, and we're finding a lot of targets that look really relevant to sarcopenia and longevity there. There's a good overlap. We also have metabolomics data, and some of these metabolites look very protective that could easily, if you wanted to think about, do I need to take a supplement? I've convinced myself, okay, these are what the squirrels are using. So there are some, I think we could talk in private a little bit more and not disclose so much, but yeah.
I'd enjoy that. I got one more question for you then, just in public. What's your next animal, may I ask? Have you decided?
Yes, the spiny mouse. So this spiny mouse can pretty much regenerate almost every organ. So.
Very, very, very cool. Thank you.
Question? Oh, one more question, sorry.
Hi, yeah. I was just wondering if the overall loss of biodiversity is affecting your long-term R&D strategy.
Not yet. But
Gotcha.
yes, something we could worry about in the future. Yes.
All right, give it up for Katie one more time.